Well, good morning, everybody. My name is Eric Marsky, and the presentation that I've got for you today is actually going to be based upon, no, it's really not a new product for us, but one that we have not covered as of yet in our webinar series, which is the ESTeem Airscope. And what this is a spectrum analyzer that we've put together that will allow us to kind of view the what's happening inside of this invisible world that we have. So probably the best place to start this is, well, really, what is a spectrum analyzer? I get it to shift here. There we go. Okay. Uh, what the good place to start really is, what is a spectrum analyzer? Well, really what this is a specialized piece to test equipment that really allows you to visualize what's happening in this invisible world, this world that we cannot see. And really what it is this is all part of the radio frequency world. The difference is that this spectrum analyzer lays out what's happening in a grid box set by frequency across the bottom and signal strength on the top. Now, it's primarily used for RF technicians, engineers, everything from analyzing signal patterns, reviewing what's actually happening in a transmitter for efficiency, modulation. It allows you to go in and view if you've got spurious emissions on a transmitter. More field type applications for it is it allows you to actually measure receive signal strengths, look for different interfering options, and really what a key element for it is looking for open frequency channels, especially when we're dealing with channels that you have to share the 900, the 2.4, the 5.8 gigahertz bands. All of these are actually shared frequency bands. So when we're setting these up and you're trying to determine which one you want to use, what you want to do is find the most open channel you can. And really, these are actually kind of laid out in a couple different types. You'll generally see them as either a bench type supply or a handheld spectrum analyzer. Um, but as you see, these are generally just one single unit where the display is actually on the piece of test equipment itself, the inputs to it, the RF head, the what's actually doing the calculation, the visualization. It's all one piece of equipment. But these are very, very expensive devices. Generally, these are starting at about $10,000 and go up from there for very modules. So what we did is we put together what we call the AirScope. Now, the AirScope, it's a fully featured spectrum analyzer. It actually will cover a very, very wide band, everything from 70 megahertz all the way to 6 gigahertz as far as resolution. It will show you both real-time spectrum analysis and also what's called spectrography. And we'll get into that a little bit. It's just a different way of analyzing what you're seeing on the screen. We've really tried to simplify it so that you don't have to know how the ins and outs of the test equipment itself. You can make adjustments to it, of course, but we've really put this into very simplified things. It does auto scaling for particular frequency bands. We put it to where you can actually record the traces and review those at some time in the future. You can also, it's basically, we put it in so you can do one button site surveys. You determine, okay, these are the bands that I'm interested in. Well, the way that we're able to provide this at a fraction of the cost of a benchtop supply is that we kind of break this into two different pieces. We actually have the radio side that actually does the receiving, does the signal analysis, and then we actually tie that into your own computer. The computer then is actually gathering the information, showing the visualization side of it, and it actually allows you then to store it. The AirScope actually comes with everything you would need to operate. It comes with the AirScope unit itself, the running software, the power supply, multiple antennas that cover everything from 150 megahertz all the way to 6 gigahertz, which is really across our entire uh, uh, product line. It also even has a GPS antenna that is supplied with it, because part of what this will do is you can actually use this AirScope for analyzing um, in a mobile environment. And so it will tell you exactly where you're at when you received this amount of signal. So if you were to drive around and view it, you can have a mapping of it that you can tie together. We will bring this up in the future, but we've actually tied this directly to, if you go to our website under AirScope Field Spectrum Analyzer, you can actually get more detailed information. We'll show you what that is here in a bit. So let's go ahead and real quickly kind of give you an idea of how this actually works. Well, hopefully you're able to see my screen here. And what we have is, just like we can bring up any one of our radios, we start with the ESTeem Discovery. This is something that you can download. It's part of our software suite. And this will then identify any one of the radios that attach to it. Just like any one of our other radios, if I hit Discover, the AirScope is going to come up. It'll show you the IP address, the mode it is, the type of radio, all the way, even the firmware version that is in that particular one. What we're most concerned about really is the IP address, because the radio and the computer talk to each other and share this information at the IP layer. So we need to make sure that the computer and the AirScope are set to the same IP subnet. If they're not, you can actually get in here and adjust the IP address of the AirScope itself or to match into that network. Well, now that we have this information, we know it's set on 172.16.8.113. What we'll then do is the software for this radio is actually all done in Java. Now, what this can do is this really then requires that you have this installed, Java installed, and also WinPCAP. If you actually install the Discovery utility, that will bring in the WinPCAP. So all that's really required is the Java engine to get that to run. This will actually, the software will open up and actually have a Java-based executable file. All we need to do is we can just double click on that executable file, and it will then open up the AirScope page. Now, this may be a little intimidating when you first look at it, but that's what we're going to do, is kind of give you an idea of what's actually happening here. For anybody that's never seen a spectrum analyzer before, the way that it's actually displayed is actually in this 10 by 10 grid. Okay, and the way it's laid out is fairly simple. You actually have frequencies across the bottom and the amount of signal strength that'll pop up here on the screen. So as you notice here, if I set this down to say, turn this down here over at 900, see, as I push the 900, what it does is it'll actually cover everything from 902 to 928 and some of the outside edges. The reason that we put that in there is that there are times when especially you're looking at these bands, there may be licensed channels outside of what you're looking to put in that may be impacting that signal. So we don't want to necessarily concentrate just only on the frequency channels that we're seeing. So as you notice here, the way that this is laid out is it's actually set by the reference level at the top being a minus 65. That means this top line up here is uh, minus 65 dBm as far as the signal. So every grid that goes below it, it's broken apart into 10 dB. So the line below it would be minus 75, minus 85, minus 95, etc., all the way down. We've also put in a couple different markers in here that will kind of help you. You can actually move this display line. And as I mentioned to you before, so if I move it up here, you'll see here, there's the minus 75. Okay, we'll see where that actually applies here. We also have a marker that works on the frequency side. So if I show you what I mean, as you notice here, our center frequency line is 950 megahertz. And the way that it's broken apart is the entire span covers 36 megahertz wide. That means each one of these blocks is 3.6 megahertz. Now that may seem a little odd, but the reason that we have that particular value is we want to be able to cover the 902, the 928, and have some of the outside edges. So if I move this marker over, you'll see here at the top, our marker number is showing up in frequency. Okay, so what we can do then is, as I move this over to say 902 megahertz, which is right about here, we see here that that's the outside edge of the 900 megahertz ISM band. And so we can actually view all the way down to that edge and some of what's happening even below it, all the way out to 895, 897 megahertz. Okay. Yeah, on the higher end, so there's the 928 marker, all the way up. Let me get it over here to 933. Okay. So overall, the grid pattern will start making a little more sense. So as of right now, the reason it's not displaying anything is because I haven't actually tied it to the AirScope device itself. This is actually just running in the software. To do this, I simply go over to the Configuration tab. I then go down to the lower right-hand corner and I see the IP address 172.16.8.113, which matches what we had on let me bring it back up here. Our discovery, 172.16.8.113. So we know that that's the correct IP address. If that looks good, you hit Save Configuration. It'll pop up on the screen, Save Configuration, and then I can simply go back to the Site Survey tab and hit Connect to Device. Now, as soon as I do this, now I've actually already connected to mine. What it will do in most cases is actually start programming the AirScope radio head. So it will go through there, it'll tell you exactly what it's doing, it's processing, it's sending the information to it, and then it'll come up here on the screen. Now, on your end, you're probably not getting the exact type of display I'm seeing on mine because it's actually running incredibly fast on mine. So what I'm going to do then is I'm actually going to try to slow this down, and I'm going to go ahead and I'm just going to disconnect from the device, and it will then stop it where it's at so we can kind of review the way that this is laid out. So each one of these lines, each one of these points, peaks and whatnot, is a point in frequency and a certain amount of signal on that. Well, everything that has an electrical current through it generates a certain amount of RF energy. The Earth itself actually radiates RF energy. This combined energy is what we call the background noise. And as you can see, this is a great visualization of what that background noise is. So if I move my marker over here to a peak of, say, 912.298 in the background noise, this is where you can actually kind of take the measurements. I can then take and drag my display line up, and at that particular instance in time, the signal strength on that channel was minus 70.7. Now, it's changing all the time. It's actually a very dynamic type of situation that we're looking at, but it will allow you to view things in real time. And that's really what the first element of this spectrum analyzer is how do we actually view things? Let me go ahead and let it run again. Okay. And what I've got is I actually have in our channel here is you might be able to see it every once in a while. It pops up and marks it here. In most cases, in most spectrum analyzers, especially when you're dealing with single channels, you use what's called a peak hold. Now, what a peak hold does is it basically looks at all of these line elements that are going across here and will display and mark the highest level that it picks up. Well, it's in a channel that is in a shared channel that's very difficult to do. Let me show you what I mean. So if I turn this on in 900 megahertz, what we're going to do is essentially it's going to start adding up all of the different packets that it sees across that 900 megahertz spectrum, and we lose a lot of the resolution. We lose a lot of what we're seeing in that band. So where this really becomes important is peak hold is really used down into single channel transmitters. Now, I've been pushing along here across the button. You see here where it says product range. We've got automatic setting for 900 megahertz. We've got an automatic setting for 2.4 gigahertz, 4.9, and 5.8. But you also can use this, as I mentioned to you, you can run this spectrum analyzer anywhere from 70 megahertz all the way to 6 gigahertz. Now to do this, we can even run it down into the license band. Say we wanted to look at the 150 megahertz band. We simply type that in, hit enter. Now our center here, this center line represents 150 megahertz wide, and we can actually then change our span, so we're looking at a much more narrow profile. And as you can see, the transmitter types actually change. That's because these are actually single channel transmissions. And this is really where the peak hold comes into it. As you can see, peak hold becomes much more of a useful tool because you can actually let that run, and then you can come over here and say, okay, well, the channel that I'm seeing right here, yeah, it's running right around this 150.163. We move our display line up, so we know that there's actually a transmitter at a minus 61.9. Okay, this is great for narrowband operation, and again, this is the way that you can run this spectrum analyzer to look for very specific frequencies and specific transmitters. But the peak hold really comes into it really down on these more licensed channels because they're not wideband spread spectrum transmitters. So how do we get around that in the 900? I'm going to go ahead and click back on the 900. We see our center frequency changes to 915 and our span moved back open again. So what we've done is we've actually put two spectrograph displays within here. The first one, which is very similar to the way peak hold works, is what's called density. Now, if I turn the density map on, what this will do is this starts looking at that frequency channel and will continuously keep adding information in there based upon the transmitters that it sees. Okay, and as you can see here, we're building kind of a profile in this band over here on the right hand side. I can move my marker over, and it's running about that 912 megahertz frequency band. Okay, well, what does that actually represent? Well, the nice part is that because we know what channels we're dealing with, we now have the ability to put in what we call markers. Okay, so somewhere in here, we want to be able to identify what this transmitter is. Now, I know it's an ESTeem transmitter because I've actually got it specifically for this class here. So I know what channel it is. But if you're really not certain, what you can do is you can come down here and say, okay, is that operating on channel number 6? Well, what it does is it puts the profile picture both on the right-hand side and an active one on the left-hand side. It says, does that match it? No, that's actually not it. I'm going to go ahead and click open up channel number 5. Oh, that actually fits the profile. So that is a transmitter that is actually operating on channel number 5. You can actually even come over here and push where it says all channels on. And what it'll do is it'll put the markers for each of those given channels. Now, as you notice here, we have a 5 megahertz wide channel. You can also, let me turn these off. Let's say we put it up here at channel number 5. It fits within our band, but if it were actually going outside of that band, we can actually change that marker to 10 megahertz or 20 megahertz wide to show you the pattern that is occurring within each one of those. So it's a very valuable tool to show you, help you identify what's actually happening on the screen. Well, this density map is fantastic for identifying what's actually occurring over a period of time. But we really don't know by looking at this one pattern actually how often that channel is being used. In other words, how many radio packets. We know there are being radio packets generated on channel number 5, but actually how many of them, how often are they occurring? Well, that's really where the waterfall map comes in. The waterfall map may be a little bit intimidating, but once you get used to seeing it, it'll start making sense. I'm going to go ahead and click on it. And what it does is it changes what we're visualizing. Instead of looking at it as a combined pattern over time, each one of these lines represents a slice in time. I'm going to go ahead and wait till one pops up here till I can get an easily identifiable packet. And I'm going to go ahead and stop. So I'm going to disconnect from the thing so it'll actually pause the transmission. So we can see on here that where it changed from the blue. Now the way that this is laid out, color is identified by the amount of signal that we have here. And it's done by proportional colors. For example, the colors will start out gray, go to purple, go to blue, then green, yellow, red, maroon, and then black. Ultimately, the darker that we get into the spectrum, the more signal there is over time. And we can see that more in the density when we go back to it. I'll show you what I mean by that. But as you can see here, we can identify there is one single packet that is operating on here. Well, it's going to be very difficult for you to see because my display is actually going to be running so much faster. But as we look at this occurring over time, we can see in here, yes, we certainly have a transmitter operating on channel number 5, but looking at it on the waterfall map, it's actually only coming and transmitting a couple times a second. So we really have a density transmitter, but we don't have one that is like processing video or streaming service or something like this. So we can basically tell the difference between the two. Let me give you an idea of what I mean by that. If we then move over, say, move out of the 900 megahertz frequency band, I'm going to go ahead and turn my markers off, go over to the 2.4 gigahertz frequency band. Now, what we have on here is we actually have multiple different channels in operation because actually our internal Wi-Fi channel operates in this 2.4 gigahertz band. So you can see here something is building at the upper end and the lower end of the spectrum. Well, if I move my marker over, this will tell me it's somewhere in that 2.53 gigahertz, 2.453 gigahertz. What does that really mean? Well, if we see it on channels, we can actually put all the channels on. It will say, okay, it's centered around this channel number 9. All right, so that looks good. I'm going to turn them all off, turn my channel marker to channel number 9, and we can see here it's much wider than this 5 megahertz wide. Is it 10? Nope, it falls outside of that band too. It's probably a 20 megahertz wide transmitter, which we know it is. We can also identify there is a transmitter at this lower end, but it is actually lower than 20 megahertz. So if we go down to channel number 1, does that cover it? Yeah, it's channel number 1, but it is actually much more narrow than 20. It's actually a 10 megahertz wide transmitter. So there's a lot of information that you can glean by looking at the density map that is really then putting this information over time. It will actually continue building this density map for the entire time that you have it operating. If you find that there's information you make a change to the network and want to see the effect on it, you can actually just go over here and simply hit the reset button, and it will actually restart rebuilding that communication into that pattern. So let me show you what this looks like more as far as more data going across this waterfall map. Um, Again, it's going to be very difficult for you to see, but I'm going to go ahead and I'm going to actually bring up and start putting a whole bunch of data across that Wi-Fi channel. Okay, so we can get more packets going there, and I'll go ahead and then stop it. So as you can see here, what I did is I went on there, and we're actually at 20 megahertz wide. Oops, sorry. It resets it when you change the marker here. So let me reconnect, do this again. Okay, and I'll go ahead and stop it. Now you can see that there are a tremendous amount more packets going back and forth, each one of these lines representing a slice in time. So we can get very, very detailed on the amount of information that we're seeing that this channel was operating tremendously much faster than we're getting into the 900 megahertz band. There's a lot more traffic going back and forth, even though the density maps look very similar over time. So let me go ahead and I'll let this go ahead and rebuild. And I'm going to go ahead and turn my markers off. Okay. This is all great. This is very, very powerful information but everything that we're dealing with right now, essentially real time. We're looking at this as an active transmitter. But what we're concerned with, and one of the most powerful features that we have in this, is the ability to save this and let it run and gather this information over a given period of time. So the way that we do this is we do this in the site survey side, and that's kind of why we listed it this way. If you go to the configuration tab, you can see on here, you can then identify which of these given bands we want it to calculate and we want it to actually save. Um, if we're only interested in, say, the 2.4 and the 5.8, we can just uncheck the 900. So we'll then only check the 2.4 and the 5.8. If you're looking at which band should I use within there, which one has the most transmitters to it, you may want to scan all of them. The only other setting we need to be concerned with is what's called this dwell time. What this is that this then says, okay, I'm going to then, it's done in seconds. So at 10, what it'll do is it'll start at 900, measure for 10 seconds, then move over to 2.4, measure it for 10 seconds, then move over to 5.8, measure it for 10 seconds, and then start over again. Okay, and it will continue doing this as long as you're running the test. So if you're running a single frequency, say you're only interested in running, say, the 900 megahertz or the 2.4 gigahertz, well, what you can do is you can actually just only check that one band and then increase your dwell time. I found usually when I'm doing field work, I just run this out to say 2 minutes, say 120 seconds, because then what it'll do is it'll measure for 2 minutes and then start over again and then go for 2 minutes and add all of these together over time to create this kind of profile map. Okay. So if all of those look good, so what we're going to do is we're going to test the 900, 2.4, 5.8, and we're going to do this for 10-second dwell time. You just simply hit Save the Configuration. Then we go back over to our Site Survey tab, and we hit Record Traces. Now, when we hit Record Traces, it's going to pop up this little menu that says, okay, what do we want to call this? Well, let's just call this Training. And we'll hit Select Record File. Now, what changes on our screen here, we can see that we are no longer just active, but we're also recording. It's now recording the 900 megahertz band, and then you see it says switch to 2.4 gigahertz. It'll record that for 10 seconds. And then as soon as it gets 10 seconds into that, it'll switch over to 5.8. Record for 10 seconds, then jump back to 900 megahertz. And it will continuously do this until you turn this recording feature off. So you can do this for hours. You can do this for days if you would like. Most of the time when we're doing the site survey work, we let this run and gather information, say overnight, for the times that you're actually not testing on those given bands. Or we might run it to let it go so we can see what's happening on, say, the outside edges of the given frequencies that we're testing. So it can be a very, very powerful tool in the recording for two different methods. So we'll let it go through one more time so we can kind of see what's happening in those given bands. And then when it switches back for this last time, I'm going to go ahead and once it gets past the 5.8, I'm going to go ahead and stop the recording. As soon as you hit stop the recording, what it will actually do is it will then close that file, add all of these different transmitters up together, and process it into a single file. Okay. The other thing that I want to show you before I switch off of here is you see down here at the bottom where it says latitude, longitude, altitude. That's actually coming from the GPS because the GPS is actually running in the radio at all, or in the AirScope at all times. I just don't have a GPS antenna. I'm inside the building. It wouldn't pick it up, but it will. If you want that information on, all you got to do is put that GPS antenna onto there, and it'll start gathering the GPS information, and it will save that GPS information also. So we've got a good picture of what's going on here. I'm going to go ahead and hit stop the recording. And now we're back to live. You see here, it no longer says record. It also doesn't say play. So as you can see, we can actually then pop between all those different bands. And the density map continues to build on each of those. So as long as you don't reset it, it will continue to bring this information in. One of the most powerful features, though, is now that we have this recording, we have an active slice in time in that radio spectrum. Let me show you what I mean by this. If I hit play file, the other window is going to pop back open again. I can select the training file that we created, which has the time and date stamp at the front. You can see it. Hit select playback. Now what we're seeing on our screen here, it says play. So we no longer are looking at an active or real-time display. We're looking at what we had recorded in real time. So I can actually pause it at any given point and say, oh, well, I see that transmitter coming up here. Where was that at? Well, I can bring this over. Oh, well, that looks good here. Our signal strength on that band was about a minus 55, so it's very, very close to me. You can also even bring up the markers. It will then tell you, okay, well, the signal strength is actually getting all the way up to a minus 52.6, so we know that that transmitter is fairly close to us. So it's a very, very powerful tool because we can stop, we can record, I can push it through in time. So if I move my little marker up, we see here is 900, can move it forward. There's 2.4, we move it forward. There's the 5.8, and I can pause it and stop it. Not only can you review this information, one of the key things is that you can share this file with anybody else that has an Airscope. So if you're recording this information out in the field and you have very specific questions, you can send it to us and technical support, and we can look at the same exact information you are at that given time. Okay? So I'm going to go ahead and let this run out. Oops. I'm going to go ahead and let this run to the end, all the way to the end, and now we are back live once again. Okay. So outside of being able to review this, again, what we're doing is we're looking at that information in real time. So you'd have to keep analyzing it and looking at it. So what we want to do is have a method of what does this look like, add it all together. So we've put in a feature in here which is called analyzing the file, and it will take that file and add all of those transmissions that we recorded, all those 10-second slices, back up and create a report as a PDF. It's very simple. We hit analyze file. The pop-up menu is going to be here. We say yes, that's the file that we want to analyze, and we hit select file to analyze. Another window will pop up here on the screen, and it will come up and tell you that it's actually generating this report. Well, instead of waiting for this to report, which I will get to, I've actually will show you what it looks like one I've done from a previous site survey that I did. I saved it into the library file, and it all comes out in PDF. So let me bring it up here to the screen, put it up here so everybody can see it. All right. So as we see here, what it'll do is it'll title it based upon the file that you've put in there, the center span, the reference level at the top point here, even show you if you've identified the attenuation that you've got there. Because if you're in a very, very noisy environment, what you can do is you can actually put the AirScope will come with a 20 dB attenuator. So if you're in a very noisy area, it actually pushes all the signals down by 20 dB so that everything isn't just at the very top line up here. So it basically over attenuates it. Mine, I'm in a very fairly noisy environment. So as you see here, I have a 20 dB external attenuation. It doesn't really change anything as far as what you're seeing on the screen. The only difference is it changes what the reference level is so that the signal strengths that it's reporting are actually correct. So if we go back to here, this particular one, I only had a 3 dB attenuator on here. But as you can see, let me back it up a little bit. What this did is this identified in the 900 megahertz band, this is an active transmitter. I've got a small little rubber duck antenna tied to the one here. This was actually tied into the antenna that was installed at the customer site. So you can actually view what that antenna, that installed antenna, is actually seeing. So looking at this here, you can see here we had quite a bit of transmissions at the 912, and there was actually above 922. This was actually a licensed channel. So when we did our testing by simply looking at this, said, oh, we've got a nice little valley here in 917, about 5 megahertz wide. We conducted the testing at 917 and didn't run into a single problem. So this gives you a great visualization tool of what's actually happening in this invisible world. I'm going to go ahead and close it. I'll bring it back up. And now if I go back to where we were before, we see here that based upon this file, it's actually created 3 different test reports. It's all laid out by time and date, and we can see here's the 915, the 2.437, and the 5.8 gigahertz band. So if I click the 900 megahertz, it will then open up the report for that. Let me bring it back over. And as you can see, it's almost identical to what we saw when we were actually running the spectrum analysis. If we leave it over time, you'll actually identify those different transmitters. So looking at this, what does this actually tell us? Well, we can see here in, say, the 900 megahertz band, at this given time, the time that we did the testing, the only transmissions were actually occurring in this 5 megahertz window at 912. So we'd probably want to set our transmitter up at 922, 917, or 907 may have a little bit more interference, but that's really going to be the key. This is really where the power of this AirScope comes into it, is it gives you this visualization. It's a fantastic tool. It's a great place to start. Overall, it is one of the key pieces on how to create and design a very reliable system. So if anybody has any questions, I'll take a look and see if anybody's got any here. Let me take a look here real quick. All right. Doesn't look like anybody has any particular questions at this time. We'll go ahead and have this available up on our website as far as if you need to come back and review it. But I really want to thank everybody for coming in today and going through this presentation. And hopefully it was instructive as it was to get. So have a great day.